Hello everyone. My name is Yangmin Wang, and I'm a PhD student from Aalto University. Today I'm going to do a presentation based on our research work in retrofit project. And the topic is sustainable retrofit solutions for Southern European residential buildings. Coming to the study objective, the study evaluated the impact of retrofit technologies on energy consumption and CO2 emissions of 3 demo buildings in South Europe. And we also analyzed the maximum energy conservation and CO2 emissions reduction with retrofit technologies combinations in different demo buildings. We have 3 demo buildings in South Europe. The first demo is a small apartment building in Athens, Greece. It has 3 floors. The first floor, or the ground floor, is a workshop, and the second and third floor are apartments. And also the second demo building is a small social house in Lisbon, Portugal. The first floor of this social house is apartment, and the second floor is a social space. The last demo is in Valladolid, Spain, a terraced house which consists of 4 apartments. Each apartment has 3 floors, and also marks the annual heating degree hours at indoor temperature 15.5 degrees in these 3 countries here, and to let you have a brief idea how much heating is required in the buildings in these 3 cities. And we can find the annual heating degree hours in Valladolid is extremely high, much more higher than 2 other cities. So it will also help how the occupant heating their living spaces. Basically, the heating schedule might be different. I will mention about this later. So in terms of building envelope properties before renovation, all of these 3 buildings are constructed last century. So if we check this table, we can easily find the U values of the external wall, roof, external floor, and external door are really high. Extremely when we compare them with new constructed buildings. They are quite high, so it means all of these demo buildings are poorly thermal insulated. And also the infiltration rate is quite high. So 2 important characteristics of these demos: one is poor insulated, the other is high air infiltrated. Regarding the HVAC system before renovation, all of these demos are naturally ventilated. And in terms of space heating system, the Greek demo and the Spanish demo were heated by boiler and water radiator system, while the Portuguese demo used electric heaters. And one thing is most important is the heating schedule. I come from Finland. In Finland, we have quite cold and long winter, so continuous heating is more commonly used in Finland, but it's totally different in South Europe. So in Greek demo and Portuguese demo, it's intermittently heated. So it means the space heating is only available several hours in the morning and in the evening. But as I mentioned before, the annual heating degree hours in Valladolid, Spain is quite high. So this is why they use continuous heating, but with varying set point. And for the space cooling, only the Greek apartment building were equipped with split cooling units, but the cooling is still available several hours in summer night. And in the domestic hot water system, they all use boilers with different energy sources. So to simulate these demo buildings and also the retrofit technologies, we choose the EDA-ICE as our simulation tool. It's the most common building level simulation tool used in Nordic countries. It allows dynamic multiple zoom simulations and modeling of building characteristics, including geometry, structure, and technical system. And the output files include building energy consumption, indoor air quality, and thermal comfort. The bottom left figure shows the EDA-ICE interface, and you can define maybe hundreds, thousands of different input data here, and it's quite user-friendly. And the right one is the example of the 3D models we built in EDA-ICE. So after defining all the input data in EDA-ICE, we can get the simulated purchase energy in these demo buildings before renovation. The top left table shows the breakdown of the purchase energy in different demo buildings. And these values are marked with red rectangular is the energy demand for space heating and domestic hot water heat. So in all of these demos, the energy demand for space heating and domestic hot water account for the majority part of the building energy consumption, although they are in South Europe. The right table shows the primary energy factors and CO2 emission factors of different energy sources in these three countries. And one factor I want to mention about is the CO2 emission factors of electricity in Greece is extremely high, almost more than 2 times of other countries. It is because it's outdated energy system. So with this simulated energy consumption and primary energy factors, emission factors, we can calculate the primary energy and CO2 emission of the demo buildings before renovation. Among all of the demos, the Portuguese social house have the highest primary energy and CO2 emission consumptions. So after we build up the demo models before renovation, then we can integrate retrofit technologies into our building model to see how they will affect the building energy consumption and CO2 emission. This figure shows the simulation procedure of retrofit technology. The basic idea is we divide the retrofit technologies into 3 packages: passive package, ventilation package, generation package. And we simulate them package by package. In each package, we follow the rule from the single technology to all of the technology in the package. And finally, we also decided 2 final combination scenarios, which means the final combinations including all of the technologies in the passive and ventilation package and either of the generation measures in the generation package. In the passive package, the first technology is bioaerogel thermal insulation. It is a thermal insulation material developed by University of Nottingham. It is quite environmental friendly. So it has a significant impact on the U value of the building envelope. For example, before renovation, the external walls is 1.0, and after renovation is 0.4. So in the simulation, we assumed all of the roof and the external wall will be covered by this kind of thermal insulation material. Then the second technology is PV vacuum window. It is a multi-glazing window with low U value and also integrated with a PV module. So the U value of the window is 0.6, and the generation efficiency is quite low, only like 3%. So to maximum the electricity generation of this PV window, we decided to install them on the south facade of all the buildings. Then the final technology in the passive package, we have the PCM. We decided to install this kind of PCM layer under the ceiling of the residential building, and this kind of material will start melt from 80 degrees and stop at 36 degrees. So it will be act as a passive cooling method during summer daytime, but it will also lead to another issue, especially in the residential building without any mechanical system. It will result overheating during nighttime. Then in the ventilation package, the first technology is insulating breeze membrane. It's also a kind of thermal insulating material, but it also have an impact on the building air tightness. Since we don't know the tested building air tightness after renovation, so we assume two cases. One case is 50% air tightness improvement case. The other one is 100% air tightness improvement case. 50% air tightness improvement case, which means the building air tightness value is equal to the average value of the building air tightness before renovation, and also the tested air tightness of this kind of materials. And the 100% is the building air tightness after renovation is equal to the tested value of this kind of materials. Since this kind of insulating breeze membrane has a significant impact on the air tightness, so it will affect the indoor air quality. So to solve this kind of issue, we put window heat recovery, also called the room-specific air handling unit with heat recovery, into our package. It's a mechanical, energy-efficient mechanical ventilation device which can be installed above the window, and it consists of several fans and heat pump which can utilize the heat from the exhaust air to heat up the supply air. So the heat recovery efficiency is about 0.76. Finally, in the generation package, one option is photovoltaic thermal system. The core of this system is PVT panel, which can generate electricity and also collect solar thermal at the same time. The conversion factor of solar thermal is like 0.5, and electricity generation efficiency is like 0.13. And then the solar assisted heat pump is heat pump, but the evaporator side is connected to a solar collector. So finally, we got the simulated purchase energy after renovation. And in the passive package, you can see the most effective measure is the bioaerogel thermal insulation material, which can bring from 16 to 43% of purchase energy reduction. If we compare the first bar group in this passive package and with these two this bar group, we can find even we add PV vacuum glazing window and also the PCM material, we don't see a huge increase in the energy reduction. So among the passive package, biohydro thermal insulation is the most effective measures. And in the ventilation package, due to the insulating bridge members' impact on the thermal insulation and also the building air tightness, it will bring the similar energy reduction percentage as the biohydro thermal insulation. And if we compare the membrane 40% case with the 100% case, we can find only 1% difference. So which means the building energy efficiency brought by insulating bridge membrane mainly come from their thermal characteristic instead of their impact on the building air tightness. And in the after we install the room air handling unit with heat recovery, it will have impact on the space heating, so it will slightly increase the energy consumption, which means the reduction percentage will be lower. And in the PVT system and solar assisted heat pump, it will bring like from 80% to 24%, and in solar assisted heat pump, it brings like 8% to 38%. So you may wonder why this solar system only reduce the purchase energy by 8% in Portuguese demo building. As I mentioned before, the Portuguese demo, they use the portable electric heaters. If you want to use the solar system, it only covers the domestic hot water, so the reduction is quite small. If you want to improve the reduction percentage, it's better to use water radiator system. So the last two bar groups show the energy reduction percentage in, after implementing final combinations. And the passive package plus ventilation package and the PVT system will lead to from 49 to 66 reduction, and the passive ventilation and solar system lead to from 46 to 71% reduction. Then coming to the CO2 emissions after renovation, it brings quite similar level just as we see in former slides, but one value I want to mention is that in the Greek demo building, the installation of solar assist pump even increased the CO2 emission, because before renovation in Greek demo we use like oil boiler system, so it consumes fuel, and after renovation we have solar assist pump, it consumes electricity. So the the energy consumption is more like we from the more fuel to less electricity. But in Greece, we have extremely high CO2 emission factors of electricity. So this is why CO2 emission increased by 1%. And also correspondingly, the final combination, including passive ventilation and solar assist pump, only reduced the CO2 emission by 30% in Greek demo. Coming to the conclusion, biohydro thermal insulation led to around 15 to 45 reduction in CO2 emissions, while the impact of PV vacuum glazing windows and PCM is much smaller. It's lower than 10%. Retrofitting with insulating breeze membrane reduces CO2 emissions by around 50 to 39%. But to maintain a good indoor air quality, room air handling unit with heat recovery is needed. Then the final reduction is like 7 to 28%, and the installation of PVT system and solar system brought up to 27 or 37 reduction in CO2 emissions. And also coming to the maximum energy saving potential with our retrofit technologies, the optimal combination with PVT system gives 48 and 58% CO2 emission reduction in the Greek and Portuguese demo buildings, and the optimal combination with solar heat pump reduced CO2 emissions by 72% in the Spanish demo building. So this is all the presentation. Thank you. Any questions or comments?
Do you have any questions or comments for Dr. Wang? Anybody? Any question? Yeah, please, yeah.
I have a question regarding the countries you have chosen. You chose 3 different countries.
Yeah.
So it's based on what climate?
So it is decided by our partner. They are coming from these 3 countries. So this project work like we simulate, and we give our simulation will give them idea how much energy consumption we can save, and they will renovate and compare the real energy consumption and also our simulated result. So they may choose the residential building which need for renovation. So this is why.
Yeah, there was also a difference between the countries when it comes to the optimal combination of your retrofitting techniques. So you think that this difference is due to the climatic reasons?
Some of them is due to climate, and more of them comes to some limitation, because some of the buildings have limitations. For example, they are not allowed to install the PV panel above the roof or something kind of like this.
Okay. Anybody else? Any question? Please, Mohamedin.
Mohamedin from University of Southern Denmark. So, I mean, the technologies that you tested are very nice and interesting, but in energy retrofitting, you will always need to combine the technical analysis with economic analysis, right?
Yes, but this kind of novel technology, some of them are just past the laboratory verification stage. It's not yet in the market, so they haven't decided the price. So maybe we'll do the cost efficient estimation later. Yeah.
Because if I'm trying those combination in Finland or Denmark, that's very expensive solution.
Yeah.
So I try to optimize it from the economic side.
Yeah.
The project has to do with innovations and looking for any new technologies which could be well applied to building, and hopefully that will lead to commercialization after the first stage is just R&D and demonstration. So it's really, I understand what you talk about, like something you take from market and put it in, but this is a European project like that, innovations. That's the key there. Okay.